That's good. Okay. Good afternoon, everybody. This talk is about the people detection module that is present in PCL, how it was, the modification that have been done, not so many, from 2012 when it was proposed, and the project that started from this module. So the other open source projects that we started from this module. So this was what you can get with executable present in PCL. So starting from a point cloud, a core point cloud, you can detect people in 3D data. And this was the infrastructure, the classes present in the PCL people module that is using also an implementation of the object descriptor as a feature to detect the person. And it's proposing a particular clustering for specific for people. And this is more or less what is present also in the tutorial that is online about this project, but how to use this software. I'm reporting here this just for showing you a little difference between how to use it now and how it is described in the tutorial, since the website is not updated because of some issues that we are solving in the next days. So after you detect the people detector object, you can set some parameters. Some of them are mandatory, so you should set the RGB camera intrinsics and give the point cloud as input, etc. But then there are some parameters which are optional, and among these you can set also some limits for the minimum person height of the person. And this has been recently removed in favor of another method which is similar, and the only difference is that you don't have to set only the minimum maximum height, but also the minimum and maximum width. So this was a minimal contribution, but since I received some questions about this, I reported this change in this Hackfest. So then the algorithm is able to detect many people within a frame without any tracking. So what you find in PCL is just the people detection module. But then this was these are some these are just a comment on the frame rate. Okay, this was an old test, and now the algorithm works at 30 frames per second, and recently, as we will see, it has been optimized also to work on embedded platforms such as the Jetson K1 and TX1 from NVIDIA. As I was saying, in PCL you can find just the detection model, but then it was used as a component of other people tracking projects, still open source. So here you can find the ROS Industrial Human Tracker, which is a combination of what the people from ROS Industrial had as people detection and tracking software, combined with the one in PCL and with some other improvements. So in this case we were using the best pipeline we find out was to use the people detection in PCL together with another in cascade in series with another people detection algorithm on detecting classifying hard features extracted from disparity image, again from RGB-D sensor. And for evaluating this, we also collected the data set in an industrial-like environment, and you can find a blog in the PCL website, because this was a code sprint sponsored by PCL and Southwest Research Institute. And then there was another extension, again at the beginning sponsored by CodeSprint and a group from UCLA, the REMAP group, and this was for extending people tracking to multiple RGB-D sensors. So taking the algorithm working from a single sensor and building the infrastructure in order to having a system that can be composed of many cameras in order to detect people in wider space and intrinsically fusing the views and the detection from many cameras. Here you cannot see very well that part, this kind of view. So there is no limit in the number of people that can be tracked, and compared to other systems, this system doesn't impose to people to wear anything, and it is all open source, so the software is in the OpenPTrack website, and the typical system cost is in between systems composed by just a single sensor, because we use many sensors, but is way lower than using motion capture or other tracking systems. But here, as in the people detection module present in PCL, what is implemented so far is just the synthroid tracking, so the tracking of the synthroid of people. A nice improvement would be also to track skeletons of people, but the remote group from UCLA is interested in this, but for now it's just a research-oriented group. OpenPTrack can be used with different types of RGB-D sensors, so it works with Kinect-1, with you, Swiss Ranger from Mesa, and you can also use custom stereo cameras, and you can use these sensors all together in a single network, so you can have heterogeneous networks. Of course, the one which works better is the Kinect-2 because of the high resolution of the depth and the time of flight technology that allows to have an error versus the distance, which is nearly constant, while structure-like sensor has the quadratic error versus distance. So this is the typical infrastructure that you have in an OpenPTrack network. So in order to process the stream from the RGB-D sensor frame by frame and don't transmit the streams from all the sensor to a central node, we perform people detection frame by frame, attaching each sensor to a processing unit, which analyzes the stream, performs people detection, and then send over the network just the people detection information, so position of people and some other information, height or whatever. While the tracking node, which is a centralized node, receives information from all the detection nodes and fuses all these people detection into tracks. So it performs the data association, which is now global nearest neighbor, where so the position, the association is optimized globally for all the detections arriving each time. And recently, all this has been ported to work also on embedded platform, as we were saying. So we showcased at the GPU technology conference OpenPTrack working with, as detection nodes, this tractor. So a Kinect-2 attached to Jetsons, NVIDIA Jetsons. It works both with TK1 and TKX1. The difference is the frame rate. So with the TK1, the frame rate of full detection is about 15 frames per second, while it is about 25 with the TX1. But these nodes are compact, so they can be installed easily. They are low cost and low power consumption, so they are ideal detection nodes for building large networks. And so what is important, what was important in order to use a multi-camera system was calibration. So the tracking node needed to know the position of all the cameras within the network. So for doing this, we have, of course, after the intrinsic calibration step of each sensor, there is an extrinsic calibration procedure, which is quite standard, as you may know. So you move the checkerboard around, and this is detected by all cameras, and their pose is automatically estimated. But then we added also, as we will see, another process of calibration, which starts with the first extrinsic calibration as initial condition, and then refine camera poses by means of people detection this time. So the standard procedure is like this. We worked a lot in order to make all the system easy to use, easy to install, because also people not from computer vision are using it, because it is targeted also for artists, creative, who wants to build immersive experiences based on people motion. So Here you can see a real-time feedback from the calibration. So when you move the checkerboard around, this is a network with 10 cameras. You see, this is the ROS visualizer because all the software is based on ROS. You can see where the checkerboard is detected in the space and how cameras frames are estimated. And because of the estimation is refined, is performed with a bundle adjustment framework each 5 seconds, and then when you save the result, this bundle adjustment is repeated once for all, and the results are saved. Camera poses are saved. And you can also have a feedback on which camera saw with how many checkerboards were seen by each camera, so you can the user can move the checkerboard close to the cameras who need to see it. And as I was saying, this is not the only calibration, because there can be still some human errors, or when you have a large network of cameras, you can have some propagation of the errors, and you end up with people detection by different cameras not really overlapping. So here you can see detection from different cameras after the first step of calibration. So each color is a different camera, and you can see you can have an offset. So the second procedure uses this as input for refining camera poses. So this is a process which internally uses the PCL registration model, so the iterative closest point, and is able to refine then the camera poses in order to make detection coincide. In this step, of course, only one person will be in the scene in order not to mismatch detection trajectories. And so this is the output that you can have on the ROS visualizer when performing tracking. So data association is based on a consistency of motion for the tracks, and here you can see with different colors all the tracks, and the tracking message is usually composed by the ID of the person, the central position and date, the bounding box, the track, some information about the duration of the tracking, the status, if the person is occluded or not, and we hope in the future to provide also skeleton information. And this is a heat map, another visualization of where people are present over time. And these are some of the installations, installations in Los Angeles done by the Remap group of the CLA. And this was composed by two Kinect 2, this with some Kinect V1, this with other 6 Kinect V1, 3 with Swiss Rangers and 1 stereo, so also heterogeneous networks. And the biggest network we built was 10 cameras, but it could handle also more. And these are some of the applications, as I was saying. It is used for art, so for building massive application that change when people move, or for education in order to show on screen some avatar of kids moving around, in order to teach to them some basics of physics and chemics, so relation between particles which are personified by the kid. And also for this is a pavilion, I can show you a little video. A pavilion of an historic park in Los Angeles that has been rebuilt. This is a project, and inside the pavilion there will be an OpenPTrack installation of 6 cameras, and this is a mock-up that was built in Los Angeles, just outside the park, but indoors in this case. These were the projectors that the beamers were used. This is a Swiss Ranger. This was the first output of the system when we tested it 2 years ago. So at the first stages of OpenPTrack, and this was the output of the cyber mural. They call this cyber mural because it's a mural where you can see photos of Los Angeles, changes over time if people move back and forth, or changes over the neighborhoods, different neighborhoods of Los Angeles if people move left and right. Sorry. This was the first application of OpenPTrack in Los Angeles, but now there is also a class from UCLA using OpenPTrack as a basis for all the student projects they do. And okay, so yeah, this was a little video. Yeah, here we were in my lab. We were using just 2 and here you can find the image with the superimposed tracks. And here there's a top view of the tracks. And here is an example with many people. And now I'm showing you also a little demo. Of course, I couldn't bring a network of cameras, but I'm just launching one, the Skinet. So that's all. Okay, so this is the ROS visualizer. So in this case, I am just showing the depth image, which superimpose the markers of the person, and here you can see the tracks in real time. So if you want to come here and give it a try.
Volunteers?
Of course, this is targeted to tracking standing people. That's why it's not targeted to detectors.
So please, volunteers, just walk around.
Anyway, what I wanted to show you, because this was just a single camera demo, is that we also exposed all the parameters of the algorithm. So with ROS there is this nice interface, nice GUI, is RQT reconfigure, so you can also vary the detection thresholds, the age of the person, whatever, voxel size, because we are using voxel filtering from PCL. You can reset the heat map. You can. There is also a. Okay, so these are the tracking parameters, and you can also. You have at the end also a filtering node, and you can choose the filtering window of the moving average filter or some other parameters that were also requested by Remap. Okay, so let's see just if the detection threshold is very low. You can see some flows. You can. It's sometimes detecting some people and switching from one to the other. If it's too high, then no detection, so the track is deleted, and so on. If you want to try, or if you have any questions, please ask.
Questions for our speaker?
Of course, if you want to contribute to OpenPTrack, it's an open source project, so. Sorry?
It's teaching people from PCL
I couldn't contribute back OpenPTrack because it was based on ROS. Contained a lot of out of core features, but of course this could involve. I was thinking also because we improved a bit the detector in some improved the detector in OpenPTrack, so I could contribute back that part to PCL. Yeah, that could be done. Yeah. It was also a bit. We had some optimization related also to highly placed cameras. So since cameras are sometimes used very, they are very high. So the detection algorithm was originally thought for mobile robots at this stage. So there are some optimization that can be done in this sense because of this perspective.
Okay. Any more question?
Yeah.
Regarding the moving camera calibration, that works on live streams or does it work also based on files?
We thought it for live streams or bags, cross bags, which are the same as live stream, more or less. But I mean, the algorithm is there, so if you want to use it with files, you need to adapt it. But we don't have an offline version actually. It's only online. But
I have a question as well. You work with multiple Kinect 1 cameras. Do you run into any trouble with overlapping patterns?
yes, if you have the cameras pointing to the same place, you can have some problems. If they point to people from different angles, this is not that bad. So we use
You solved it by pointing in different directions.
well, this is maybe intrinsic in a computer, since you want to enlarge the field of view, seeing people from different angles. So there are no cameras placed one close to the other or in the same direction. So as I showed, no, well, I don't know if I have a video here, probably not. But I mean, yes, there was an installation that I showed, just a picture.
6 cameras.
Yeah.
6 Kinect 1s, so probably one from
And
front,
we
one to
didn't-
the back. So you have overlapping parts on the floor.
Yeah,
But
that was not that important, because the most important part was people.
And how did you filter mismatches on the ground plane then?
Well, computer just removed the ground plane, so we were not interested that much in the points from the ground plane.
I don't know your experience, but I've been surprised at how not terrible interference is. Like, everyone knows theoretically it's a problem, but I've definitely seen things that have multiple cameras with some decent overlap, and it doesn't just become terrible data, you just start to lose a little bit more.
Yeah, in everyone, if you have interference, you don't see some points because they are filtered out. But this was happening mostly on the ground plane, and we were not. Our aim was to estimate the ground plane and then remove it. If the ground plane is not seen, we use either the last frame estimation. We don't refine the ground plane if we don't have enough points, or we start up. If you don't see the ground plane, it could be that if the ground plane is shining, we use information from the calibration in order to use that as a reference.
You mentioned you have an extra step for the calibration.
Yeah.
Is that correlated to the number of cameras which are being active at the moment? In a sense, one of the cameras goes down, or an additional cameras added, do you have to recalibrate the system?
Well, this is the calibration refinement process.
Pipeline. At which steps of the calibration pipeline do you have to recalibrate in case of changing the number of cameras?
Well, calibration is done as first. Then if you change the network configuration, you need to recalibrate, but there is to perform again the first step of calibration, where all cameras are calibrated with the checkerboard, and then if the calibration is not good enough, you can do the second step with the refinement with people detections. And there is also an option to calibrate just one camera or a certain number of cameras that you choose. So if you have one camera moving that moves, in the meanwhile, you can just calibrate that one with respect to the network that you know that is calibrated. So there is an option in the configuration file with which you can lock one camera, the calibration of one camera or more cameras when you're doing calibration. And this is also the case if you want to add a camera, you don't need to recalibrate everything.
Okay, guys. Thanks a lot, Matteo.